Not able to dodge bullets like Neo? Well, you should consider giving Kevlar a shot. Kevlar is a para-aramid synthetic fiber that was developed by Stephanie Kwolek in 1965 at DuPont. It is well known for making up bulletproof vests, but it is also found in fireproof clothing, certain types of tires, soldiers' helmets, and cut-proof gloves. The material has a very high tensile strength to weight ratio, 5 times higher than steel. Development of this polymer has been transformative in the military, space, security, and even recreation industries. Because it is extremely strong yet lightweight and flexible, its properties and applications are unique. The chemical motivation that preceded the development of Kevlar was liquid crystal behavior monitoring. This led to the development of Kevlar because under shear forces, as liquid crystal solutions pass through an orifice, the randomly oriented polymer chains become fully oriented in the direction of the shear forces and become associated with other chains in near-perfect molecular orientation. With this knowledge, scientists at DuPont hypothesized that polymers that can be driven to a particular orientation using these mechanisms could be designed to be very strong. Kevlar is a polymer that contains benzene rings linked together by amide groups at the para position. This results in the polymer being flat and rigid because of the location of the constituents on the benzene rings. Kevlar doesn't melt, but it decomposes at 427 to 482 degrees Celsius. Its density is 1.44 grams per centimeter cubed. Because it contains amide bonds, Kevlar is sensitive to acid. Kevlar is made from a condensation reaction of terephthalic acid and p-phenylene diamine. Each of these can be prepared from benzene using electrophilic aromatic substitution reactions. To make the diamine, we will start with benzene and add sulfuric acid and nitric acid. The nitro group will add onto the benzene ring via electrophilic aromatic substitution. A hydrogen on the ring will be eliminated by a base in the solution to regain aromaticity. This group is then reduced using hydrogen gas and palladium on carbon to an amine, which is electron donating and therefore ortho-para directing. The second nitro group now adds via the same mechanism as the first. It is again reduced to an amine using hydrogen gas and palladium on carbon. The terephthalic acid is made from the diamine. The amine groups are converted into diazonium ions using nitrous acid. The diazonium groups are then hydrolyzed using water and hydronium ions to carboxylic acids to form the terephthalic acid. This and the phenylene diamine are condensed using hydrochloric acid. The carbonyl on the carboxylic acids becomes protonated, which makes it electrophilic, so the nitrogen can act as a nucleophile by using one of its lone pairs to add into the carbon. An intermolecular proton transfer occurs between the alcohol group and the amine during the tetrahedral intermediate, which then collapses down as water leaves, forming the amide. This process repeats to elongate the polymer chain. When the concentration of polymers is high and the precursor material is extruded through a small spinneret, the polymers align and bundle together. These interactions depend on long polymer chains that contain oxygen, nitrogen, and hydrogen atoms that are capable of associating through non-covalent hydrogen bond interactions between polymers. This is largely due to the para-orientation of the amide groups that makes the long, flat polymer chains possible while also enabling the non-bonding interactions. Since its development in 1965, Kevlar has become integrated into many aspects of modern society. From the front lines of political protests to the behind-the-scenes research at NASA, Kevlar has transformed polymer science and redefined what types of materials are considered strong.